Welcome back, ladies and gentlemen, to another exciting video. Today, our focus is going to continue on unit number 2, where we are going to focus primarily on the structure of solids, primarily the structure of ionic solids, metals, and alloys. So the key thing here is going to be able to differentiate on how the atoms are arranged and how they interact with each other in each of these solids. In addition to that, it's also going to be important to recognize the strength of the bonds within these solids and be able to rank them based off of properties related directly to Coulomb's law. So without further ado, let's get started. Hopefully by the end of this video, you will be able to explain the structure of an ionic solid, determine when ionic compounds can conduct electricity, describe how metals bond, and determine when metallic compounds can conduct electricity as well. Furthermore, we're going to be able to differentiate between two types of alloys, interstitial and substitutional. So let's start off by talking about ionic solids. Now, ionic solids are solids that come from ionic compounds, and they are organized in a way to minimize repulsions and maximize attractions. Well, what does that mean? Well, take a look at the right-hand side here. We have sodium atoms, positively charged sodium ions that are located in the middle of the crystal structure. But notice they are completely surrounded by negatively charged chlorine ions. The chlorine ions themselves are completely surrounded by positively charged sodium ions. So that's what I mean when they organize themselves in a way that maximize attractions. If two ions of a negative charge, such as two chlorines, were next to each other, well, they would repel one another. But what the structure does is it organizes itself in a way that maximizes those attractions and prevents those repulsions from happening. Now, ionic solids are made of ions, and they alternate in their structure, creating what's called a lattice structure. So you see how they kind of alternate. We've got chlorine, sodium, chlorine, sodium, chlorine, sodium in this lattice type structure. They're very, very strong, that they're going to be held together with a variety of strong intramolecular attractions. The relative strength of attraction is based on the atomic radius and relative charge. Again, going back to Coulomb's law. The closer those ions are to each other, the stronger those intermolecular attractions are going to be, as well as the relative charge as well. Positive 2 ions are going to have a stronger internuclear attraction than positive 1 ions are. So let's take a look at some example problems and think about how we can determine which of these lattice structures are going to have the highest intramolecular force and therefore higher boiling point and higher melting point. So which of the following compounds would have the greatest lattice energy and therefore highest boiling point and highest melting point, and justify your response? Well, let's take a look here. We have sodium chlorine, sodium fluoride, potassium bromide, and potassium chloride. So all these have a positive 1 and negative 1 charge, so we really can't determine it based on the magnitude of the charge, but we can determine it by atomic radius. Remember, the smaller the radii, the closer the nuclei are going to be to each other, and as a result, the stronger the attraction is going to be between the individual nuclei. So between sodium and potassium, sodium is at a lower energy level and therefore would have a smaller atomic radius, and between all the halogens that are there, fluorine would be the smallest. So the greatest lattice energy and therefore the highest boiling point and highest melting point would be sodium fluoride. Each individual ion has a +1 or -1 charge, so the two ions with the smallest atomic radius would have the strongest bond. Na has a smaller radius than K, and F has a smaller radius than Br or Cl, so NaF would have the smallest bond difference, and therefore highest lattice energy, higher boiling point, and higher melting point. If I look between these other two, we have NaF and MgO. Well, F and O, when they take their ion form, have a relatively similar radius. Same with Na and Mg, but the only difference here is that Mg and O are positive 2 charges and negative 2 charge, and Na and F are a +1 and a -1 charge. So the strongest here is going to be MgO. Both Mg and O have +2 and 2- charges respectively. There's a negligible difference in atomic radius, so Mg and O will have a stronger attraction due to the magnitude of their charge being greater, which results in higher lattice energy, as well as higher boiling point and higher melting point. So remember that the strength of the lattice energy is directly correlated to the melting point and boiling point of those ionic solids. So by looking at the radius as well as the magnitude of the charge, we can determine which has the greatest lattice energy and therefore which has the greater boiling point and the greater. Let's go back and reflect on the attraction between the positive and negative ions of an ionic solid. Those attractions are very strong, and that makes ionic solids very brittle. So when a strong enough force is applied, the lattice actually shifts, resulting in similar charges being near one another. This is something we discussed in a previous slide. This causes a clean break in the substance. So when you actually break ionic solids, you see actually a very clean surface when it breaks. So you can see in the example here on the right, when those negative charges and positive charges are forced next to one another, they're going to repel each other, thus resulting in a very clean break, which results in ionic solids being considered very brittle. Now, ionic solids have a very high boiling and melting point. Now, keep in mind that ionic solids cannot conduct electricity because those ions are held in a fixed lattice, so those electrons do not have the ability to move within the lattice structure. However, ionic solids that are melted or dissolved in water can conduct electricity because now those ions are free to move, whether they are in a liquid form or whether they are dissolved in solution. The strength of the electricity that can be conducted is completely determined by how many ions we get when we dissolve into solution. Things that dissolve into more ions are going to have more free-flowing ions and therefore have a greater ability to conduct electricity. Let's talk briefly about metallic solids, and we've discussed this previously, but metallic bonding is represented by positively charged nuclei that are surrounded by delocalized electrons. A term for this is sea of electrons. Now, these electrons are free-flowing, which allows for the conduction of electricity. And since the electrons are not bound within bonds like covalent or ionic bonds are, then the metals are ductile and malleable, and those electrons are able to freely move within the metallic solid. Additionally, these also have high melting points as well. As you're sure you know that metals don't just melt in your hand, except for gallium. Gallium's weird. Gallium's actually kind of cool because you can. Gallium's melting point's like right around human body temperature. It's a little less than that. So if you take a little cube of gallium and put it in your hand, it melts, which is really kind of cool. So speaking of metals and going in a little bit further, we could talk about alloys. Now, alloys are metals that contain atoms of other elements, so alloys are not pure metals. Alloys tend to make metals less flexible and more rigid, typically because, especially when we look at something like an interstitial alloy, which forms between atoms of different radii, smaller atoms that have smaller radii tend to fit in between the individual atoms of the metal itself, thus making it less flexible and less ductile because there are metals that are taking up that space that is in between the individual atoms of the metal. And so that typically makes it much, much stronger. A good example of this is steel. Steel is an alloy of iron and carbon, where carbon has a much smaller atomic radius. They tend to fit in between the iron atoms, thus creating a very strong alloy. A substitutional alloy is different because they form between atoms of a similar radius, where one atom tends to substitute for another. Example of this would be for brass. Now, brass is an alloy of copper and zinc, and those are right next to each other on the periodic table. Copper is number 29 and zinc is number 30, so they have a very similar atomic radius. So as a result, we would consider brass a substitutional alloy because the atomic radii are similar, and therefore atoms of one metal are simply going to replace another when they form that particular alloy. So hopefully you're able to understand and explain the structures of ionic solids and metallic solids, understand when they conduct electricity, and differentiate between alloys. Pretty straightforward video today. Hope you've enjoyed it. If you have any questions, let me know. Make sure you like, comment, and subscribe JLand Bio for more exciting chemistry content. Have a great day. We will see you soon. Bye-bye.